The combined use of the first and second derivatives are pretty powerful, and I will exhibit that with these 4 examples. So suppose you have a local maximum, like at this point. So let's think about what the derivative should look like at this point A. Right, this is where your local maximum is. Now, the derivative goes from positive to negative, right? So at A, it's 0. So qualitatively, it does this, positive to negative. Maybe it's a straight line, maybe it doesn't look exactly like this, but it has to go from positive to negative because the slopes are positive, 0, or negative. Okay. Now let's look what the second derivative looks like at A. So if it helps, we'll give this function a name, f. You have that f prime at A is 0. And what's f double prime at A? Well, again, you just look at what's happening. What's the slope at A? The slope at A is negative because it's a decreasing function. So at A, the second derivative is negative. So it's some point here. Okay? Now let's look at what happens at a local minimum. Again, let's call this point A, this x value. Now we have that the slopes are going from negative to positive and 0 at A. So negative to positive, let's say like that, and 0 at A. F prime of A is still equal to 0. But what's true about the second derivative, f double prime at A? This is a positive slope. So it's greater than 0. Let's say a point here. Now let's take a look at this situation. I've made this very flat so that the derivative at A is 0. But notice what happens before and after A. The derivative is positive, it goes to 0, and then it's positive again. So it's positive, it goes to 0, and then it's positive again. How about the second derivative at A? Notice the second derivative at A must be 0. So it's right here. This is called an inflection point. And this is where the concavity changes. So at a local max, the concavity is down. This is concave down, concave up. This is concave down, and it switches to concave up at the inflection point. Finally, let's look at this example. Let's make this our point. Again, A. What's going on at A? Well, the first derivative is not 0, it's negative. So in this whole entire interval, the derivative is negative, 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 negative. So it's decreasing and then increasing again. So my first derivative at A is negative, right? But it was initially low and negative, and then high and negative, and then low again. In other words, this is the most negative slope. So it's something like that. This is what f prime looks like. So f prime at A is some negative value. It's some negative value, but it becomes less negative to more negative, and then less negative again. So f double prime at A is also 0. So f double prime at A equals 0 at this point. This is also an inflection point. Even though the first derivative at A is not equal to 0, the first derivative at A is negative here because the slope is negative. But the concavity changes. From here to here, the concavity is down. Concave down switches to concave up. Concave down switches to concave up. Here the concavity is the same, it's all concave up, and here it's all concave down. So we've gone from knowing what kinds of points we have, max, min, inflection, inflection, to information about the first derivatives and second derivatives. But the point is that it goes the other way too. If we have information about the first derivatives and second derivatives, we can understand what kinds of points we have. And I'll give that example right now. So now we can take a look at the function f of x equals x cubed minus 27x. So what does that function look like? Well, first of all, the coefficient of the highest power is positive, so you know what happens for large and very small x. So you know that the function should look something like, actually let me remove the axes, should look something like this, something like that. But you don't know exactly where where this curve lies on the xy axis. So let's start finding the critical points. F prime of x equals 3x squared minus 27. If we set that equal to 0, we'll see that x is equal to either negative 3 or 3. Great. So we can put coordinates on the local max and local min. The x coordinates are negative 3 and 3. Let's see what the y value is. F of 3 is 3 cubed minus 27 times 3 equals 27 minus 27 times 3 was negative 54. And by the antisymmetry of the function, f of negative 3 we know equals 54. So now we can draw this function. Negative 3, 3, and this isn't going to be quite to scale. Should be much skinnier than this, but this is 54, and this is negative 54. And that's what the function looks like. Now we happen to know that cubics have this shape. But if we didn't, and we just knew that we had this maximum and this minimum, okay, how would we know the concavity here? Well, we could take the second derivative. The second derivative is 6x. The second derivative at the value 3 is 6 times 3, which is 18, which is positive. So that means you have a concave up point right here, or region at 3. F double prime at negative 3 is negative 18, which means you have a concave down region at negative 3. And notice that F double prime at 0 equals 0 right here, and this is where the concavity changes from concave down to concave up. So you can compare the values, right? At a local max, the second derivative is negative. And here we have local max, the second derivative is negative. And at a local min, second derivative is positive. Local min, the second derivative is positive. And then at an inflection point, the second derivative is 0. At an inflection point, the second derivative is 0. So negative 3 is where you have a local max. 3 is where you have a local min. And 0 is where you have an inflection point. So we're going to look at another example of using the first and second derivative, and this example will probably be more indicative of the power of the first and second derivative because most people don't know what this function looks like. All right, so let's see if this function has any max or min. First derivative is e to the x plus x e to the x, which is e to the x, 1 plus x. We're going to set that equal to 0. This is never 0. E to the x is never 0, so this function, this derivative is only 0 when x equals negative 1. So what kind of a point is that? Well, we're going to have to take the second derivative to find out. F double prime of x is, again, the derivative of this, which is e to the x, times the derivative of this, which we already know. E to the x, 1 plus x, which equals e to the x times 2 plus x. And when we plug in negative 1, we get that this value is still positive, right? It's just because it's e to the negative 1, which is a positive value, times 2 minus 1, which is 1, which is e to the 1, which is 1 over e. Okay, so we know that this point must be a local minimum because because at negative 1 we have a concave up region. Okay, so we know that we must have this kind of a behavior. But where does that exactly occur? Well, we're going to have to plug in negative 1 into our original function. So f of negative 1 is negative e to the negative 1, which is negative 1 over e. So now we can draw the function. Negative 1, we have the value negative 1 over e. So that's a very small value. Okay. We also know that the function at 0 is just 0, so that's another data point. Moreover, so we have this concave up. We know that the function goes through 0. Both these functions increase as x increases, right? So we know it's got to do something like that. Moreover, for negative values of x, right, or rather values of x which are smaller than -1, the first derivative is negative. So again, for values to the left of -1, values smaller than -1, this is negative. So we know that we have to have a decreasing slope down to -1. This is our minimum, and then it increases after that. We don't know exactly how it increases, but we know it increases. So there we have it. We have a rough idea of what this function looks like using just the function itself evaluated at the critical point, the unique critical point of the function, which is where the first derivative equals 0. And the second derivative helped us understand what kind of critical point we have. We have a local minimum